When we left off, we had all of the switches and diodes placed on the PCB, and now we were going to place the rest of the components. So primarily, we want to choose a location for the USB port and the controller, and everything around the USB port and controller will kind of fall into place. So I want to place my USB port in the top left here. It's a typical location for USB ports in TKLs. And I'm also going to line up the top of these mounting point pads, these ovals, with the top of the switch, right? So I want them to be within the switch footprint, and then I want it to be on that notch, and then right in the center between them. So I have the same distance on either side of the USB port between the two switches, between the escape and F1 keys. Now I want to take the rest of my components here and kind of group them by which passives go with which components and vice versa. So let's look at our schematic, and I want to group first, the USB port. So I'm going to find R2 and R1, our 5.1K resistors, and put them up near the USB port. So we'll move those and we'll put them up near here. And next, we'll take our 3.3 volt regulator and we'll find U2 and U1, and we'll put all three of those components together as well. So there's U1, and we'll take C1 and C2, and we'll put them near the 3.3 volt regulator. This ESD and then the JST connector for the unified daughterboard, those two components will also put up near the USB port. So we can have a JST connector kind of face to the side here, and then the ESD can come off of the data pins, right? And we're going to look at the reset switches too. I'm going to put those in places. One of them needs to go, the boot needs to go near the flash, and the reset needs to go near the RP2040, along with their pull-up resistors, right? So the reset switch has a 5.1K pull-up resistor, and the boot select switch has this resistor that needs to go, you can see where the air wires are pulling it. It's pulling it kind of towards this Q select pin on the flash, and then towards one side of the switch. We'll get these two 5.1Ks, and that goes, on the Q select, and then up to 3.3 volts. A crystal with its capacitors and its 1K resistor. Okay. And the next passives are, well, there's the flash chip, right? And its 1U capacitor. All right. And then we have the RP2040 and the RP2040's capacitors, right? So the rest of these capacitors belong to the RP2040. Right? So I think that's basically all of our parts kind of broken up, right? So the C8 here. Take the RP2040 and its capacitors. Okay. And we have R8 and R9. What are these? We select R9. The data pins. So let's put those near the RP2040 as well. So these air wires, these blue lines, you can turn them on and off with this show board's rat's nest. It shows you what connections need to be made. And so when you make a connection, right, it will, the air wire will go away. And that was a terrible connection. The RP2040's pitch is 0.2 millimeters, or the width of its pins. So if you go to track use net class width, you can select a predefined size, and we'll edit this, and we can make a predefined width that's 0.2 millimeters. So now when we go to route, it's too wide, so it kind of collides with the other pins. But if you hit the W key, it'll make it thinner, right? So now we can make connections that are the right width without colliding with other pins. So I'm going to try to place components around the RP2040 It's not really placed in the rest of the keyboard yet. We're just going to place them around 2040 to see where they need to go. So I know that this D- pin needs to go near near this pin 46, and the D+ resistor needs to go near pin 47. And these terminating resistors, you kind of want them to be close to the RP2040 and not close to the USB port, right? When I move them, if I'm just moving the mouse around, it snaps to the grid, but if I hold control, I can place them anywhere the mouse goes, right? In a kind of infinite grid there. So the flash chip, it has its 3.3 volt pin, needs to be near its decoupling capacitor. And then the flash chip pins, like we saw in the other video, are off to this top right of the RP2040. So you can see these pins on the RP2040 go directly to the flash chip pins, right? More or less. We'll get there. So there's IO3 and the clock and IO0, right? So that's this location for the flash chip is good because it's close to all the pins that it needs to be close to. And I'm going to delete all these wires because they're quite terrible. All right, so that's that. Now the next thing is the crystal, right? So we're doing this in priority of highest speed to lowest speed. USB runs at 16 megahertz, the crystal runs at 12 megahertz, and the flash runs at, I'm pretty sure it's 1/2 of the crystal speed. I'm pretty sure it's 6 megahertz, but it might be 12. We want to line up all of our crystal pads and the capacitors along with it such that this net and this net have very similar lengths, right? So we have X in and X out, or X out on the left and X in on the right. And then we want X out on the left and X in on the right, which we do. We have X in here and we have the other X out net here. But that goes through this resistor, right? So I actually kind of want to rotate this by 45 degrees. Now, you may be saying, well, when I hit R, it rotates by 90 degrees. I actually set in my board setup, I think it was in the board setup, and it might not have been. But there was a setting, preferences, there we go. Preferences, where in the PCB editor, I could set this step for rotation to be 45 degrees, right? So I kind of like working like that because I like to put the crystal at 45 degrees relative to the RP2040 so that the X out and X in traces are very similarly sized, right? That's the same length as that, basically, right? So I can move this capacitor to be kind of in line with this trace, and this resonating capacitor has a ground, and its respective net is all right here, right? I'm doing this net highlighting by selecting the pad and then hitting the tilde key. And this capacitor likewise has its nets close by. So try to find a good spot for these capacitors. Looks like, ooh, that's nice and tight. I like it. So this cluster will be wired up to this X out and this X in, right? So that's how that's going to be wired up, and it's good to have everything right close by. And this ground's going to come around. All right, so you kind of get the point where you're minimizing the distance of these traces. So all of our grounds are now connected. Boom. All right, so everything's connected here. I'd want to add some ground vias later, but we want to minimize the trace length to the components, to our passives, and to our other components, right? So by minimizing the trace lengths of these high-speed components, it ensures signal integrity and all this great stuff. The next thing on the bottom side here, we have our SWC, SWD, and reset pins, which are what we broke out to this header here. So we know this header is going to want to be, somewhere close by. This seems like a pretty good location for it. And the anatomy of this RP2040 is such that there's power, USB data, more power, and QSPI along the top. That's all there is. On the bottom, we have the reset, debug, some power, the crystal, and then in the corner here, you have 4 I/O. You have 2 more I/O on the left. And then the sides are all I/O. Right? All of these pins are I/O except for these 4 power pins. And the only ground connection you have is this ground pad in the middle. And then this test enable pin, pin 19, that's right here. So in that ground, you're going to end up wanting to short directly to the pad, and then that's also going to be like your single ground connection for your crystal, right? The next thing is to line up a capacitor with every power pin. And the output, the 1.1 volt rails here, one of these, I forget which one, is the power regulator output, and the other one is the input, and then this one is just like a reference. So we need, this 1U pin is on a 3.3 volt pin. Actually, I like to put the 1U, it's kind of the larger capacitor, in this 3.3 volt corner. And then the 10U, this large 2.3 volt bulk, we'll have it kind of upstream coming off of our voltage regulator. So you can see I'm not actually making any connections right yet. I am just laying out where the capacitors need to go and laying out where the components kind of need to be placed relative to each other. All right, so here we have a setup for the 3.3 volt regulator. We have this 5 volt input, a shared ground net, and then 3.3 volt output. And then that output will go to this bulk capacitor, and the bulk capacitor will then go to this 1U, and then that 1U will spread 3.3 volts all the way around to the rest of the pins, right? That's kind of the overview of the power traces here. So let's continue placing these capacitors around. 100 nanofarad on this 1U capacitor or 1U pin. Another 100 nano, 3.3 volt on that side. This one's probably on this pin. This one's on this pin, right? 1U. Let's move. All right, it's not letting me move this one. All right, well, hold on. Don't know if you caught that, but I actually hit the N key by accident. It changed the grid size. And when I tried to move it, there wasn't a grid position close enough by. So I had to just change the grid size back. So hitting the M key is what you want, right? Not the N key. All right. There's our 1U capacitor for the 3.3 volt rail, or the 1.1 volt rail here. Okay, so there's a slight problem, right? So we have this 1 volt, it has a capacitor, 3.3 volt. There's no capacitor for the 3.3 volt here, so we're missing one 3.3 volt capacitor here. And here we have a 3.3 volt capacitor for this pin. We don't have one for these 2 pins. We don't have one for these 2 pins. So I want 2 more 3.3 volt capacitors here. I want 1 more 3.3 volt capacitor here. And I'd like a second 1.1 volt capacitor here as well. So let's add 3 more 3.3 volt and 1 more 1.1 volt capacitors to the schematics. And what you end up finding out is that the schematic and the PCB are always going to be living documents, right? Until you get the whole design finished, you won't be definitively saying, okay, the schematic is done, because it won't be completely done until your PCB is done and you know you don't need to make any more changes. There will always be times where you will find yourself needing to go back and make a revision to the schematic, or adding something or taking something away where you didn't think of something before, right? You kind of overlooked maybe the scope of something, or you overlooked a pinout. So it's always important to keep in mind that the schematic can change even as you're doing the PCB. And so we just added 4 more capacitors. So, so let's move those into place. All right, so we've got the 1.1 volt here, 3 volt here, and another 3 volt. Here, and another 3 volt down the bottom. All right, so I'm liking the look of this so far. Let's go through all of the passives, make sure we have them all in place. So this fuse we know needs to go up near the USB port. And then we have these resistors here on R5 and R4. Those are for this boot select button. Okay, so this is all in place. This boot select is Q select pin here, so we can move it over on this side. And then the reset button, it kind of goes on this bottom right or bottom left corner near this reset pad. So we have all of our pieces kind of roughly in place where they need to be. You have 3.3 volt power coming in from the top left, and then flash on the top right with the boot select to the right of that. Crystal near the bottom, your SWD breakout in the bottom left, and your reset pad breaking off of that. So all of our I/O is going to come out to the left and to the right sides, and we can actually rotate this whole thing around, right? Doesn't really matter how it's oriented, but that's the general layout where components need to go on this RP2040 design. So from the USB port, we have these air wires, right? We have the data lines, ground, 5 volt. So USB data, which are coming off these resistors here, and then 5 volt power, right? So there's USB data, 5 volt power, all of this is coming up right off of the USB port. So that's where our USB comes in, and then our matrix connections and our peripherals come off the sides of the RP2040. So the next step is to find a place for all this. Again, the spacebar is really spacious. There's a lot of area here to put things. And with the data pins coming off the sides, it kind of makes sense for the pins to be more oriented, like between these switch layers, right? So have these traces that will come up around the switches. So I think that's kind of where I want to put things. And then we just have to move all the rest of the components around to fit in that space. But I'm going to get to that in just a little bit, and we're going to route the USB port next. So let's get these resistors sorted. I'm going to put the R1 on the left and R2 on the right. This just lines up with these air wires, these thin blue lines. And I can connect those CC pins up to the resistors. And then I can connect the D- and D+ sides. If I'm not liking the way it's hitting the grid, I can hold down the control key to place it more finely. And I like to make just a slight bend here, like a little loop around the D- and D+. One goes up and one goes down. It doesn't really matter which one is on top and which one's on bottom. Now this, because we chose pins 1 and 6 on the ESD chip, These should be able to line straight up through the middle of this chip. D plus will go there and D minus on the left side here. I also like to kind of bring the D plus line, or bring this so they're side by side, and then go to route differential pair. Select either one of these nets, and sometimes it says can't find a suitable starting point. So we can just make kind of a like force it to start like in that location. Then we route differential pair. Sometimes it works. And sometimes you have to start from the pads of the ESD chip. All right, here we go. So bring it up close, and then we connect the rest of it by hand. Like that. I also like to bring these tracks in like this, right? Then we can still route the differential pair here and bring it out through the chip. Again, I'm going to replace these kind of generated tracks with a simple straight through, and then delete kind of the bulkier parts of this. There we go. Now this will also line up with our JST connector. If the JST connector is pointed like the same way as the USB port is pointed, you can just pass it right through. But I like to have my JST connectors pointed like in line with the direction of the rows and columns, or the direction of the keys, right? So I will be routing this differential pair through like that. And the reason we route differential is because these traces need to be matched up lengthwise, the USB data traces, because they are the signal type they are needs to have similar length traces and similar impedance on each of those traces. So you want these to be these two traces to be as similar as possible. Sometimes I like to actually just make these completely horizontal. It's not ideal to have 90-degree traces like this, or I guess stubs off of these lines, but USB 2.0, especially the high speed or the full speed or whatever the lower speed is for USB 2.0, doesn't really care about the stubs, right? It's pretty resilient. For VBUS, I want to use a thicker net class, so we can go ahead and add another net class width here and add a 0.3 millimeters. This will increase the current carrying capacity of that net. Same deal here. Try not to hit these holes, and also try not to hit the other nets nearby. And all these grounds can be connected together as well. Now, the VBUS line needs to go to this fuse, and the fuse needs to go to the JST connector. So let's do that. And then let's add a ground trace to the CC lines with a via that connects them. I'm using the letter V key to add these vias while I'm running the trace. The 5-volt line needs to go to our ESD and ground to that ground point there. Then we connect, and then using the V key when I'm not running a trace switches which side of the copper I'm on. We can connect that ground pad to some of the ground pins on the USB port. So now all of the grounds for the CC lines, the ESD chip, and the USB port are all connected with either this red trace or using vias to the blue side. Likewise, we want the ground connection on our JST connector to connect to this ground point as well. So we are bringing the 5-volt line along with this differential pair down to our chip, right, to our RP2040. So this will be our 3 traces, the 5 volts and the D plus and D minus, that we will need to bring down to the RP2040 through all these switches. So kind of be conscious of where the traces are and where they need to go, and kind of sketch out a path. I'm going to go ahead and sketch out a path using the 5-volt line. It's probably going to be something to this effect, right? Coming down through like this. Let's try to get these components placed. So the RP2040 and its surrounding capacitors, you can use the selection filter here to only select footprints, along with the crystal, all need to be placed very close to each other. We'll have the crystal near the edge of the board. It's probably bad for EMI reasons, but it's good for laying things out. Now the voltage regulator can go somewhere before this, so we can bring the 5 volts to the voltage regulator, and then the 3.3 volts can go down to the RP2040. And then the bulk capacitor and 3.3 volts can go before all of this. The reset circuitry, along with the header, go in this bottom left near this stab. And then our ROM with its switch, I'd want to place between these 2 switches. That looks pretty good. So let's get the ROM first with its decoupling capacitor. And then the reset switch, or the boot select switch, somewhere nearby. All right. Now, so here we saw there was an issue with me dragging the position of this switch. We can select all the switches and then lock them in place, especially if we like the position of the switches and the diodes. So let's go back to our schematic, select our switches, diodes, and stabs, right-click on that, and then select on PCB. Now they're selected on the PCB, we hit L to lock them in place. So you'll see they're highlighted purple, which means they're locked in place. If you go to the Objects tab, we can unselect the visual for locked item shadow, which will make that purple go away, so it's not quite as distracting. But now, unless we select the locked items checkmark, we cannot select switches, and if we try to drag them, there will be a locked items, and it will ask us to override the locks to drag. This protects us from moving the switches around and the diodes and the stabilizers, unless we absolutely need to. So we won't have any accidental screw-ups with the layout of the PCB physically. So I want to try to route this QSPI flash, as well as the USB and power data lines coming through from the USB port. All right, so I've routed the 5-volt trace from the USB port along with the USB D plus and D minus lines using that differential pair tool, down to the voltage regulator, and down to the D plus and D minus resistors going into the RP2040. At the voltage regulator, we have a ground connection connecting the ground pins of the voltage regulator and the capacitors. As long as we have, as well, we have this ground vias. Make sure there's a really nice tight ground connection between all these components. The 3.3 volt trace we're also going to take down alongside the USB data lines and goes to the bulk capacitor. And then from the bulk capacitor, we can distribute that to the rest of the 3.3 volt pins on the RP2040. So I'm going to go straight into this 3.3 volt corner that I talked about, with these 3 pins. And then through their capacitors, down to the pins. And we can make these connections a bit smaller using the W key. And short those. The 1.1 volt connection, of course, and kind of connect all of these capacitors up. And the same for these data lines for the USB ports. And all of these ground connections can be shorted, and we can use ground vias to attach them to a currently non-existing ground plane. So let's go ahead and make that ground plane now. We'll add a filled zone, and we're going to surround the whole thing with a front and back layer ground net, solid fill. Double click at the end to finish off this shape, and hit B to fill. Now this, of course, it will be the shape of the whole filled zone, but if we want it to be just the shape of the PCB, we need to add an outline to the PCB. So we can hide the filled zone on the left side here by show only zone boundaries. And then we can go to the layers tab, and in the edge cut layer, we can use the rectangle tool to draw a rectangle. I like to go in one grid point inside the switch footprint, and then draw a rectangle across the whole board. And then taking these, selecting all items, we can take these 2 edges, and we want to fillet these lines and use a radius. I like to use about 3 millimeters. So that gives us a nice curved edge on this corner. And we can repeat the process. Well, actually it did it for the whole rectangle, so that's perfect. So now when we hit Alt 3, we get a 3-dimensional view of the board, and we have this nice rounded cornered board. There are a few 3D models in here for some of the switches that we placed that aren't 1U, which is great. And we can see we have our debug header on the bottom here. And if we flip it over, our RP2040 and the reset switches where we placed them. We can also see how the filled zone makes this light green, where that goes around our USB data lines and all of such. So now when we do B for the filled zone, it refills it, we can view that zone. It goes all the way up to the edge, but no further. We can hide the zone again and continue routing. Just a note, when we put a ground via in, that connects these ground points through this red filled zone. So when we're looking at this side, the blue zone that's filled is disconnected by this 3.3 volt trace and these data pins, but when we put vias through, now they're connected to the back side, or the front side rather. So even though they're cut on the blue side, the vias allow these ground connections to happen on the red side. hide that. Let's try the flash and the crystal. Let's do the crystal first. I'm going to do ground, connect all these together, and then right through the diagonal middle of the crystal. And then we can do these oscillating sides. I'm using the slash key to change the direction of the flip. So when I hit slash or like slash question mark, it changes the flip direction. And that'll go straight up to the controller. X in, similar, comes down here into the capacitor. That's really all there is to that. Of course, we have these capacitors for power, and the SWC and SWD pins. Now, it can't really get out of here, not enough space. So we need to back one of these capacitors up a bit. We want to make sure that the blue outlines don't cross, or we'll get a red error for them touching each other. We can back this capacitor up, probably up to here. And we can route this X out trace closer to the crystal. Gives us more room for the capacitor. Likewise for this, bring it in close, but not overlapping. Then this 1.1 volt trace can be even closer to the 3.3 volt capacitor. Delete these traces. And that'll give us room for the SWC pins to come out to the debug header. So we still need a little bit more room. And still a little bit more. Seems it's going to be a pretty tight fit, get everything in. There we go. We still have the reset trace. So it seems to me that we need to move everything over so we get this reset trace out. Let's undo all our tracing here. And you'll notice that there's a lot of undo and redo in routing these boards, right? They're living documents. You cannot say, oh, it's done, we'll go on to the next until everything's done. Because there might be some time where something else needs to be changed. I can move these down and away. Also move this SWD header in just a bit so it's not being cut off by the edge of the board. I can bring this reset pull-up resistor out of the way as well. Okay. Now if we bring reset in as close as we possibly can, we still want to be able to use pin 27, right? Maybe. And pin 28 for I/O. Then we have reset, SWD, so you're already having issues there. SWD, SWC, now 1.1 volt, 3.3 volt, X out and X in. So this is going to be a pretty tight rub. Let me try to move some things around. All right, we have these 1.1 volt, 3.3 volt resistors at 45-degree angles now, so that there's plenty of room to route to them. And then X out still lines up perfectly, and X in can come around and have not taking up any space. And we can still route this ground pin to a via. and these I/O pins out to where they can be used. In fact, we can really bring this out here, and this out here. Let me tidy this up. So these 4 I/Os. I have plenty of room. Put the ground via right there in the middle. Connect these two, put them on ground, and then connect all of these to another ground via through here. Another one for the crystal. So this is all connected to the ground plane. And it's especially important not to disrupt the ground plane underneath the crystal. So let's go ahead and route those grounds. Kind of give the crystal a protective area of ground. Then we can route the SWD, SWC, and reset pins to our header. And we might even want to rearrange the header such that it's easier to get to all these pins. So I'm going to route the SWD and SWC on pins 3 and 2 and kind of swap their places with ground at 3.3 volts. So let's go to the schematic and then swap the places of these and the ground and 3 volt. Save that and then update the schematic. SWC can come down and connect directly. In fact, let's do SWC, SWD reset, which is the same orders that come off of the IC. Update. So SWC on the blue side, SWD, and reset. And then we have, these are IOs that we can use for the matrix. So we have reset here, which goes to this button. We can put the ground on a via. And the 3.3 volt of the pull-up resistor, let's actually spin this around. Route the reset to the top of the resistor. And the 3.3 volt directly to this breakout pin. And because the ground is already in a through-hole component, it acts like a via. And finish off these 3.3 volt rails to their respective capacitors and add ground vias. I'm angling these up and down to get away from the IO that needs to come out through here. And last but certainly not least, let's get this QSPI. We'll move it down and out so we have some room to route traces up and around. As a 3.3 volt capacitor, it'll come off the same 3.3 volt line as this pin, just because it's close by, with the ground via as well. Now, I think we actually want to flip this around. There's 6 connections to make onto this chip. So I'm looking at the air wires to see which way it makes the most sense to connect them. I think this is the most logical. These connections can go, just looking at the way these 6 connections need to run, right? Let's get rid of this decoupling real quick. These 3 pins connect to these 3 pads, and then these 3 pads connect to these 3 pins. I like that a lot. Let's see if this will work. So let's move this decoupling capacitor over back to its 3.3 volt pin up here. And let's try routing these QSPI lines. Give ourselves some more room. We need quite a bit more room. So let's move these capacitors out of the way. Without overlapping the blue. Cyan outlines. We can have all this room for our QSPI. Wonderful. And these 3 can be routed around the back. There we go. The 3.3 volt line needs to go to its capacitor. And this trace come out to a via as well. Then we'll connect all of the 3.3 volt lines together. So these 1.1 volts here, and at the bottom, we'll connect these top to bottom with a via, and we'll connect the side-to-side ones with a short trace inside the RP2040 footprint. We'll find somewhere to put a via for this 1.1 volt. I'm going to go back to our interactive routing settings and go to highlight collisions just to see where I need to move things for this via. So it looks like I can put it here. I need to move the 3.3 volt via farther away. Get the 1.1 volt one in there. 3.3 volt can go here. Then down here, I need to put a via on this 1.1 volt line. That's going to be quite large, but it can fit here. I just don't want to put it on the pad of the capacitor itself. So let's move this ground connection away. Move the capacitor itself out and away from the via. You don't want to put vias in pads because, well, it just kind of creates a big headache. Let me connect the 1.1 volt line to the capacitor again. There we go. And then this connection we made on the red layer, like that. The rest of the 3.3 volt connections will happen also inside of the RP2040 footprint. So we can make these traces, come off of these pads, and then just bring it around and visit every single node that needs to have 3.3 volts. So just like that, all of our 3.3 volt lines are connected except for this one here. And again, we can do this with a VIA. VIA doesn't want to be between these two traces. We need to find another way to get this 3.3 volt connected. So the other option is to move these capacitors out just a hair. Delete these overlapping traces. And then use another 1.1 volt VIA to connect the 1.1 volts all externally. And then get rid of the inside connection. That way 3.3 volts can be connected inside the RP2040 all the way around. It's kind of a mess through here, so let's clean this up. Lovely. Okay. So 3.3 volt connected, our 1.1 volt connected, and everything is, all the grounds are connected. The last thing is this 3.3 volt here needs to connect to something, right? So I'm just going to route a short trace across the QSPI, place a VIA, and drop it into this pin here. Now the last thing grounding wise needs to be the central pad. So let's add a VIA to the center. I also like to add a VIA off in the corners. So I'm going to change my grid origin by placing the grid origin at the center of the RP2040 and changing the grid size to 0.2 millimeters. Incidentally, this is also the spacing between the pins, so we can get a nice lineup with the pins on RP2040. Then we can place VIAs for ground. We add a freestanding VIA. We can place them in the corners of our RP2040 central ground pad. And for that, I'm going to move this vertical trace for the 1.1 volt line to the side. So now we have these ground pad VIAs that will ground the RP2040 from within. We also need to route the 3.3 volt trace to the debug header. We'll again use a little VIA here and route that up to probably up through here. I just want to get it out of the way of routing the the traces for these data lines. So don't put anything on the bottom layer right in front of the MCU. So I believe that's everything routed. The reset switch for the boot select. So we're going to use the air wires to line these resistors up in a way that makes sense. We know that this needs to connect to this side of the reset switch. Then we can rotate this around so the Q select lines line up. And then this intermediary between these two 5.1K resistors line up as well. Put the Q select line, route that down to the Q select on the SPI flash. And the 3.3 volt needs to connect to this net somewhere. So I'm just going to bring it down alongside. And we're going to bump this out just a smidge. Okay. And that's our reset circuitry for the boot select switch. Okay, so everything's routed except for the matrix. Every single switch needs to connect to its diode, and I like to connect things to the center of these switches, such that if a hot swap socket is rare, but if a hot swap socket gets loose and rips these pads out, the plated holes are still connected to these traces. So you can still solder a switch to the hole itself. So I'm going to connect every single switch to its respective diode. So as I go through, I've connected all of these switches using the net class width, which is 0.25 millimeters in the bottom left here. I'm just panning with middle mouse. I'm going to get the last few here, and then we're going to talk about the multiple layouts sharing the same diode. So I'm going to start with the caps lock key because it's the simplest. Let's finish off this right. Okay. We have this diode, which we need to connect to these two switches. Now, ideally, these two switches would connect to each other, and then that to the diode. So let's figure out which net needs to go where. Right now, it's showing me that this switch wants to connect to the diode from the left side, but I kind of want to connect the diode to this pad. Then I want to connect this pad to this, and this pad to that, and so that all of these are connected together. So going back to our schematic, on the split caps locks, whichever one is selected here, say it's this bottom switch, I want to flip it such that the pin 1 goes to the diode instead of pin 2. So I can just rotate that around. And then I also want pin 1 of this to connect to pin 2 of that, and pin 2 of this to connect to pin 1 of that. The way they're in parallel, but they are flipped. That means when I save this and update the PCB, now we have air wires that are telling us to connect these two and to connect these two, which is exactly what we wanted. And that connects to the diode. So actually I want this to snap between these two dots. That's a bit better. Here I'm using the 79375 grid. So I'm going to do that for the other multiple layouts. Like I want these two pads to connect, which is 1 to 1, and then 2 to 2, and then 2 to diode. And then here I want 1 to diode. So for split shift, we want 1 to diode, which is this switch here. And rotate it around. And then we want 1 to 1 for these two. That'll be the left shift, the left of the split, and then the left shift. This is the right part of the split shift. This is the left shift 2.25U. This is the left part of the split shift. And it seems to me that these have kind of come off the grid. I'll move this whole thing back onto a grid position. Okay. These are 1 to 1. Okay, so that should be those diodes sorted. Here we are. This connects all the way across the top. And that goes to the diode. And then these connect to each other. I'm using the control key to get right between these two holes and connecting their pads. And this goes to diode there. Wonderful. These I want to be 2 to 1s, so these are all flipped connections. So we'll flip it. We'll move it like that. It's kind of busy through here, but it's okay. Now we have these connections on the outside, and then these connections to the diode. We'll do that in the same for these split space bars, or the 2 different space bars, and then all of the right side switches as well. All right, so I've made all the changes we needed in the schematic. We've got the ANSI and SANGAN bottom right. We've got the right shift, and we've got the split backspace here. So in the PCB, we can route, like say you did the split backspace. Like that. Split right shift, same deal. Clean this up a bit. It did look a little weird. Still looks weird. There we go. I'm going to flip this around to get that diode. And all of these bottom rows here, the bottom mods. Seems like these connections are right, but they're flipped with respect to the diode. Okay, so we'll just take all of these and rotate them around. The intermediary connections are correct, and they can just connect to the diode directly. Wonderful. So let's check. First, let's rebuild our zones with the B key. So now they avoid the traces we've placed. And real quick, we'll check our DRC using this design rules checker box. And the first thing I want to look for is any unconnected items before we start writing our matrix. Let this load. Okay, so we have some unconnected items. We're missing a few ground connections and a few connections throughout the middle of the PCB. So let's look at the ground connection first. We've got a zone on copper 1 and a zone on front copper as well. So this is on the red copper. It looks like there's missing zone connections, like there's an island. Kind of hard to tell where that is. Not really telling us. I don't see any visual copper islands. Zone ground on front copper and zone ground on front copper. Interesting. Oh, I do see this missing. Right, this is a ground zone that's not connected, so let's add a ground via. The bottom of this package is plastic, so we can add that. Let's see if that fixed it. It did. Okay. We're missing a few connections here. So, oh yeah, I forgot to route the spacebar. So the first thing to check always is these unconnected items, because unconnected items are the worst. And we can route this around the top. And hit run DRC again. Running the DRC should refill the copper zones. It does. Okay. So there's nothing unconnected. Of course, we don't have like the rows of the diodes or the columns connected in our schematic, so the DRC won't check for that, but that's okay. Now we'll look at the errors. Looks like we have some errors about hole clearance violations. Now these are intentional, right? We went over this last video. We have these intentional hole clearance violations for the hotswap socket and the stab holes. And likewise, we have hole clearance violations for overlapping footprints as well. So these go through all the stab holes. And then we have the hole clearance violations for like the courtyards overlapping, right? These sockets overlap each other, supposedly, but we know that these won't interfere, so we can ignore these as well. So we have all these like hole clearance violations where these holes are too close together, but in reality, we know that these will not be an issue. So we could ignore all of these violations. Also have these board edge clearance violations where the screw hole for the stabilizers seems to cut through the edge of the PCB, but in reality, that's not going to be an issue, right? So the hole is actually the outline of this inner black circle, and the edge of the PCB is this white. So there is a bit of material here between. And in reality, if this busts through and there is an opening or a gap, the screw will still have plenty to grab onto. So that's not going to be an issue. Right, so all these stabilizer cutouts, and the same for the USB port. USB port needs to have solder around the top edge here, but it will, even if it overlaps the edge of the PCB a little bit. You can, on the edge cuts layer, like draw out a little bump, right? And then move this edge over here, and then make a new one that connects it. Right, so, and then refill the zone, right? So that will solve that issue, but then you have to design your case around a little bump that protrudes out. Arguably, you're also designing the case around the USB port, so that will be okay. So, in fact, I think we'll leave it like this. And then all these are like holes drilled too close together, right? So we have these overlapping holes. That's okay. And the thermal relief zone is incomplete, right? So let's look through here. We have these thermal relief zones around the pads of the capacitors on the ground fill. I want to hide a few more of these layers. I only want to show, let's turn off the silk screen because that's getting in the way, and these user comments. What is this text? What layer is that on? It's on BFAB. Let's turn off BFAB as well. We can kind of see our copy here a little clear. They said incomplete thermal relief zone. I can't really tell what we're talking about, right? Some of the errors are kind of cryptic. I do want to connect these back to the ground pads explicitly. Let's run that DRC again and see what we're talking about here with this thermal relief zone. Just working through these errors, right? Okay, so it looks like that thermal relief error isn't there anymore, right? Okay, let's zoom back out so we can see a bit more what we're doing. And then they have this rear solder mask bridges items with different net. So this has no net, while this has a net for going to the diode. So the net is like what electrically is connected to. If this is no net, and this is the diode net, or D29 net, then yes, this opening in the black opening, right, is, well, that's not really the solder mask, that's for the fill zone. But there's this thin yellow line, and then there's the opening for this hole, it's the hole itself. They overlap. Of course, we don't really, it doesn't matter to us as much, but if we're talking about an aperture, like, see, these are both no net, so when it says they overlap, well, of course they overlap, the nets overlap and the holes overlap, so that makes sense, right? Now, if they were talking about like the solder mask aperture of these pads, that would be an issue, right? Because you could have some shorting, but it doesn't look like there's going to be any issues there. There were a few ignored tests, but I think these tests don't apply usually to PCBs, right? So if the footprint has no courtyard defined, it's probably intentional. And through these cyan lines, you can see these courtyards, right? The bottom courtyard. For all of the things that we care about, that is defined. If there's a plated through hole inside the courtyard, well, sometimes that's the case, right? So these vias or these pads are plated through holes, and that's intentional. So if we ran that test, then every single footprint would be flagged. Same thing for the non-plated through hole inside the courtyard. Well, if we look at the USB port, we have the courtyard, and then we have these non-plated through holes, and that would flag that error, even though it's not an error, right? And then the footprint component doesn't match the footprint pads. Well, that's saying if the footprint component is, say, like this, it's supposed to be an SMD, right? The footprint keyword is SMD. The 3D shapes say it's SMD, but if it had a through hole connection in it, then it would flag this error, right? So the USB port is an SMD USB port, but it has through hole pads. And likewise for the hotswap sockets, we have, it's an SMD part, right? It's soldered with surface mount assembly, but it has the through hole connections. So that would also flag the error, but it's not really an error because that's the intended use case. So we've ignored those tests. So we can go through and manually check all 98 of these errors, but it looks like these are all hole clearance violations for intentionally overlapped components, or overlapping courtyards for like these switches that, of course, we want them to be overlapped. There are multiple layouts. So it looks like all of these errors are acceptable. And then through the warnings, we have unconnected track ends, which is a bit unfortunate. We can clean those up. Then we have silk screens being clipped by the board edge. Of course, not really an issue. And then we have the footprints that don't match their libraries. So we can go through and change these. But because the footprints were drawn from our footprint selected tool, and we specifically chose them to not match what was the default, this error is okay as well. Same for these silk screens clipped by the solder mask. We can move or delete these silk screens later. I think that might be the rest of those warnings. Is silk screen warnings. Yeah, they're all silk screen warnings, all silk screens overlapping, not being legible. And as long as we're okay with that, I mean, that's okay. So we have these copper sliver issues. So what does that mean, right? It means that there is a pad that is being cut by a hole. And here, this is intentional. But if it were somewhere, like if I had a hole that was too close to some of the pads on these RB2040 or on these capacitors, right, that could be an issue, and that wouldn't be intentional. So that's our DRC. We just want to make sure we're going through all of these warnings, all these errors, and making sure that everything here is either by design, or if there actually is something messed up, we can fix it running the DRC. So let's go for a complete overview here as we hit the hour mark. And in the next video, we'll route the matrix. So our USB, we have the short connections for the D plus and D minus. And then the VBUS goes inside the USB port. The VBUS is traced down to the fuse, and the fuse goes to the ESD chip and the JST connector. D plus and D minus are routed with a differential pair through the ESD chip and through the JST connector. And then ground we've connected with vias to our CC resistors and down to the JST connector. We'll also put a via here as well. The 5-volt and data lines travel down through the switches to the 3.3 volt regulator, which also is connected with ground vias for all of the components, all the capacitors. And then the 3.3 volt output from the regulator goes down to the bulk capacitor, which also needs a ground via. And the bulk capacitor then distributes 3.3 volt power to the rest of the board using a 3.3 volt rail that's inside of the RB2040 footprint. All of the capacitors on those 3.3 volt pins have ground vias to connect to the ground plane. 1.1 volt rail has its own distribution network on the top side with vias to its capacitors, and then the data lines go through terminating resistors to the RB2040. The flash chip is positioned such that the pins that connect it to the RB2040 are lined up nicely, so when you can route them, they're just on the bottom layer, and they route nice and neat. And there's a decoupling capacitor there too with a ground via. The Q select line goes up to the boot select switch with its resistors stacked such that all the traces are nice and neat. The crystal is in a diamond formation with its capacitors and ground connections on vias, and then the through resistor going to the X out pin. There are also decoupling capacitors for the 1.1 volt and 3.3 volt rails here, which the 1.1 volt is connected via the top layer in the red line, and the 3.3 volt is connected internally inside the RB2040. The SWD, SWC, and reset switches or nets also go down to the breakout pin, so we can program or reset the bootloader externally. And then the reset line is also connected to the reset switch, so we can reset the board when we're flashing firmware. The 3.3 volt connection for this header is also connected through a trace. We've left room on all the I/O pins to route them out through the sides, right? And then we've also left room on the bottom corners to route these final I/O pins, right? And we've put all of this in a way such that the USB traces are nice and parallel to each other. And the QSPI traces are nice and neat and don't go through vias. And the crystal traces are kept as short as possible, also somewhat matched in length, right? So the length from the bottom capacitor to the pad, they match between these two routes. That's RP2040, that's the USB port. And we've also connected every diode to their respective switch with the multiple layouts connected as well. And we've gone back and forth through the schematic to make these connections in the correct orientation. That's all for today. We will get the matrix routed last in the next video.